Pascal's triangle is often introduced in the context of the binomial formula, and it's also used a bit in probability theory. Now, what these two things have in common is that they both use combinatorics. Probability theory obviously uses it, and the binomial formula has this n choose k factor, which I'll explain what it means later. What I'm going to do in this video is that I'm going to first of all very briefly explain what is Pascal's triangle. Then I'm going to explain why the values in Pascal's triangle are exactly the same as the values in this combinatorics triangle. Using that, I'm going to derive the binomial formula, and then in the end I'm just going to, as a little bonus, try to explain the problem of points and how that uses combinatorics. Okay, so Pascal's triangle is kind of an adding triangle, or as I like to visualize it, an adding staircase. What you do to find it is that you start out by writing out this staircase in boxes, and it continues forever. This is just one portion of Pascal's triangle. So in the first three boxes, you just arbitrarily write 1, 1, 1, 1, and you can do the first down the first column. Now, to find the value of any other box, you look at a box, then you say, what's the value of the box above it? This is 1. Then you're going to plus that with the value of the box 1 above it and 1 to the left, which in this case is also 1, so we get 2. Then we have here, what is 2 plus 1 to the left, plus 1, it's 3. 3 plus 1, that is 4. Then, to get the value of this one, what's 0 plus 1? Nothing plus 1, that's 1. Same here, same here, same here. This also explains why it's 1 down the first column, because what's 1 plus 0? Same concept. And then you can continue it here, you get 3 here, you get 3 plus 3, that's 6. 3 plus 1, that's 4, and you continue this process. Okay, what is n choose k? So before I answer that question directly, I want to start with a test example problem. Let's say I have 5 items laying on my desk, and I have a bag, but there's only room for 3 items. How many different unique combinations of items can I have in my bag? Well, in the first room, I could choose 5 different items to lay here, so I'm going to write 5. In the second room, I've already chosen one of the items, so I could choose 4 different ones. And in the third room, I've chosen 2 of them, so I could choose 3. How many total combinations are there? So the way to think about this is that at first you have 5 choices. Bam, 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 and bam. Now, at each one of these possible choices, you have 4 new choices. Not 5, because you already picked one item. So you can say this here, this here, this here, this here. Very just quickly, lazily writing these out here. And at each one of these possible choices, 2 items, you have 3 items to choose from. You can say 1, 1, 1, dingle, dong, dong. So as you can see, this is a decision tree. So to find the amount of combinations, we just count the branches, which is of course 5 times 4 times 3. But there's a problem. Let's say I went down this path, chose the goat, this chose the magnet, and this chose the pen. Now let's say I went down this, chose the magnet, this chose the pen, and this chose the goat. I'm at 2 different branches, and we counted the branches, and I took 2 different paths, but I end up having the same exact items. This is because the multiplication method we used counts different orderings of the same items. This, what we found here by counting the branches, is called the amount of permutations. To actually find the amount of unique combinations, we need to kind of remove all the repeats. And we do that by dividing by the amount of ways you can order, in our case, 3 items. And if that doesn't make sense, just kind of try to think about it a little bit, and then it might make sense. To find the amount of ways you can order, in our case, 3 items, because there's 3 items in our bag, you just use the exact same logic. You have 3 open spaces. In this first space, you can choose 3 different items to put here. In the next space, you've already chosen 1, so you can choose 2. And in the final space, you've already chosen 2, so it's 1 is just 3 times 2 times 1. So calculating this in the first example that we started with, we have on the top the amount of permutations, which is just going to be 5 times 4 times 3 divided by the amount of ways you can order, 3 times 2 times 1. This cancels out and we get 10. Now that was just one example. Let's now say that we have n items and that we have k spaces. What I want you to try to do is find a formula that calculates the amount of combinations. Alright, assuming that you have had a go at it, we know that we have k open spaces, so we can kind of just draw out some open spaces here. Just continuing this pattern here. At the first open space, we can pick any of the n items. At the second one, we've picked one, so it's n minus 1. At the next one, it's n minus 2. We can just continue this all the way down to n minus k plus 1. We're not taking the whole with us. And then, in the very end, n minus k. If we imagine that decision tree in our head again, we know we have to take the product of all of these. So we just say this times this times this. And then one might be tempted to say, okay, this is easy. We just say n factorial. But this is not correct because we're just timing down to the n minus k. We want to cut off the last k factors. So since we want to cut those factors off, we just say divide this by n minus k factorial. Now, what we just found is, of course, just the permutations. We have to find the combinations. So we need to divide this by the amount of ways you can order k items. And the argument that we made last time when we had 3 items is that you had these spots and you started with just the full amount. You started with k here and then got one small, it was k minus 1, and you just continued this all on the k spots here. So you could probably find it reasonable that the amount of ways you can order k items is k factorial. And when you have this and do a little algebra, then you get that this is the same as n factorial over k factorial times n minus k factorial. This is the formula. This formula is used a lot, so much we don't want to write it out every single time, so we usually just call it n choose k. And this is often denoted either as this, quite usually. You have this brackets here and then you have nk, or it's denoted as subscript n capital C and then subscript k. Not many people use this, but if you do. And you really need to think about this name, n choose k. If I had 5 choose 3, then I have 5 items. How many ways can I pick 3 of those items? Let's say I have these 4 boxes here, and I want to find out how many ways can I pick 2 of them. Well, that's going to be 4 choose 2, which is, of course, equal to 4 factorial over 2 factorial times 4 minus 2 factorial, which is equal to 6. And as you can see, there are indeed 6 ways you can pick out these boxes. Or, as another example, let's say we're playing a game of tails and heads, and you wanted to figure out in how many ways could you get exactly 2 heads in 4 throws. So, let's say we have these 4 dots here, and let's just imagine that each dot is an event. It's a throw, so you could either get a head here, or you could get a tails. There's just as big of a chance of getting a heads here as there is here and here and here. This means that the problem of figuring out the amount of ways you could get 2 heads actually comes down to a problem of asking, okay, I can pick heads from any of these possible events, but I can only pick 2. How many ways can I do that? Well, that's easy. It's just going to be 4 choose 2, which is equal to 6. Okay, now that we've hopefully understood the power of this n choose k factor, the next critical step is to understand how it's related to Pascal's triangle. As we'll figure out, it's not just related to Pascal's triangle, it is Pascal's triangle. These 2 staircases are equal. That's a statement I'm making. I'm not backing it up, but I'll do that very soon. So that means if I go to any box on Pascal's triangle or staircase, and if I go to the same box on this staircase over here, I'll see the same exact value for every single box, and it continues forever. As you'll also see, every time I go one row down, the n value increases by 1, and every time I go one column forward, the k value increases by 1. They are both centered at 0, 0, and there exists a 0 element. This means that if someone asks you, okay, on the 98th row of the Pascal's triangle, what is the fourth element? Then you have to say 98 minus 1, choose 4 minus 1, and you'll find your answer. This also explains why the first column is only 1 and the upper diagonal is only 1, because with the first column you're saying if I have n items and I'm picking 0 of them, obviously it's always going to be one way you can do that, by not picking any of them. And if you have n items and you have to pick all of them, there's only going to be one way to pick all of them, and that's picking all of them. So that explains why the first column on this staircase is equal to the first column on this staircase, and why the upper diagonal here is the exact same as the upper diagonal over here. But what about all of the other boxes? How do we know they are identical? Well, we know it because of an important combinatorics identity that we have to look at and then prove. And it says that if you have n choose k plus n choose k plus 1, then you end up with n plus 1 choose k plus 1. Alright, so to give an example of the identity I just stated, if you have 13 choose 8 plus 13 choose 9, you can just say 14 choose 9. And same here, you get 100 choose 76. And here you get nothing special, because this sum doesn't fit the form of the sum up here. To prove this, we can actually just use algebra, because we know what we actually have to prove here is that n factorial over k factorial times n minus k factorial, this is the first term up here, plus again n factorial over k plus 1 factorial now, and then n minus k plus 1, which is just n minus k minus 1 factorial. We have to prove that we can manipulate this and then somehow get n plus 1 factorial over k plus 1 factorial times n minus k, and this minus 1 is gone because it's n plus 1 minus k plus 1, so n minus k factorial. What we end up doing is that we say, okay, first out we factor out this out n factorial, and then we say n minus k here, this is the same as n minus k times n minus k minus 1 factorial. K plus 1 factorial, that's the same as k plus 1 times k factorial. And this means that we have over here some shared factors. This is a shared factor, and this is a shared factor. So we end up getting this factor here that we're timing by, this is unique to this term, and this is unique to this term, so we get this. Now, I can time the numerator and denominator by k plus 1 on this term, and then on this term time the numerator and denominator by n minus k, and this gives me a shared denominator, so I can get this factor here to be n minus k plus k plus 1 over n minus k times k plus 1. And these cancel out, and I get n plus 1. And when I then time by this over here, I end up getting n factorial times n plus 1 over k factorial times n minus k times k plus 1 times n minus k minus 1 factorial. This up here, it obviously simplifies to n plus 1 factorial. This here and this here, same thing, that goes to k plus 1 factorial, and this here also simplifies to n minus k factorial. K plus 1 factorial and n plus 1 factorial. And this is what we wanted to prove. So, we have understood and proven this identity over here. How does it help us explain that these two staircases, infinite staircases, must have the exact same elements? Well, to even attempt proving this, we must first more rigorously and mathematically define what are these staircases. And to do that, I'm going to use some new notation. Let Vij be the value at the box in the ith row at the jth column. So V tree 2, we center it at 0, 0, where 0, 0 is this. So V tree 2, the third row, that would actually be this, and the second column, that would actually be this, because this is 0, 0. So this here would be equal to 3 in this case. To define Pascal's triangle, we first of all have that J must be lower or equal to I. This is what makes it a staircase. And then Vij must be equal to, this is what we discussed in the start. You need to go up one box and then one to the left and then take their sum, and then you get this one down here below. So we have Vij minus 1j plus Vij minus 1j minus 1. We also know that the first three boxes must be 1. So we see 1, 1, V 2, 1, and V2, 2 must be equal to 1. This up here, we've defined it so again, j must be lower or equal to I, and then we have Vij must be equal to I choose j. From this here, we know that 0 choose 0 is 1, 1 choose 0 is 1, 1 choose 1 is 1. So this fact here, that's confirmed. That's same property up here. Now we just need to show this here is the case. So we need to show that I choose j is equal to I minus 1 choose j plus I minus 1 choose j minus 1. And this is what this tells us, just slightly differently. So this is also proven. So these two must, per definition, be the same. Okay, so at this point, we've pretty much understood all we need to understand about how Pascal's triangle is related to combinatorics. Most things you'll see from now on that are somehow related to Pascal's triangle are really just related to n choose k and combinatorics. Because if you have to find n choose k, making Pascal's triangle is often a lot quicker than actually calculating it with the formula. That asks the question though, why is it that the binomial theorem is related to combinatorics? It tells us how we should expand a binomial to a certain power n, but what does that have to do with combinatorics? That doesn't make much sense. Okay, well, let's just first of all give an example of binomial theorem. Let's say you have a plus b to the third power. I could expand this by saying a plus b times a plus b times a plus b. And then I could FOIL this first, and then the result that I would get, I would then time by this, and it would get quite messy quite quickly. Or I could simply calculate, and I'm saying simply with very far stretched meaning of that word, 3 a 3 minus k and b k. Then I could just formulaically calculate this, and this is quite useful for when you're doing proofs. Now, when we expand binomials, we obviously get these constant coefficients. In this case, it's 2 on the second term. Here it's 3 on the second term and 3 on the third term. Understanding where these constant coefficients comes from helps us understand why the binomial formula is the way that it is. Okay, so what I've done here is I've gone through the actual expansion process, and I've only combined like terms in the very end. This final form, before I actually combine like terms, is what I'm now going to refer to as the full expansion form. Now, I've also color-coded it, and before I say anything else, I want you to just kind of look through this and see if it all makes sense to you, if each single step makes complete and perfect sense. So, let's try to ask this question. What is the degree on each term if the power over here is n? Well, we know if the power is 2, the degree on each term, the amount of variables, is 2. Then, if the power is 3, you just time this by a factor of a plus b. You can time into the parentheses, and you get that each term has a degree of 3. You can then time this by a plus d, time into the binomial again, and you get that each term would have a degree of 4. So you can kind of do the same argument again and again, and you get that if the power is n, each term is going to have a degree of n. So we say n is equal to the degree. Now, let's also ask this question. What is the amount of terms if we have a plus b to the power of n? Well, if a plus b to the power of 2, we have 4 terms. Then we time this by a plus b to get a plus b to the power of 3, and we time into the parentheses, so we double the amount of terms. Each time, we're going to time into the parentheses and double the amount of terms. This means that the amount of terms, is going to be equal to 2 to the power of n. And this fact that each term must have a degree of n is pretty interesting, because let's try to look over here. In our case, in our three-dimensional case, each term must have this form, where I say blank times blank times blank. And on these blank, you can either have a or b. So you can have these types of different terms over here. And I'm counting this one as different to this one, even though they have the same amount of a's and b's, but they have them in different orders. Now, the amount of different terms in this form you can have is you can have 2 choices here, 2 choices here, 2 choices here, so it's just going to be 2 times 2 times 2. That would, in the general sense, be just 2 to the n power. So, the amount of different terms in this form you have is the amount of terms you have in the full expansion. And just looking at the process here, we can say with quite a lot of certainty that each term of this form, if you have a plus b to the power of n, is represented exactly once. Now, that is quite amazing, because if we want to find out the coefficient of a squared plus b, then we are simply looking at the amount of terms in this form that have 2 a's and 1 b. And to find that, we're just going to use combinatorics. We have 3 spaces, and we want to have exactly 2 a's. We know the b is going to be picked no matter what if we have 2 a's. So we just say 3 choose 2. Same thing if you have a b squared. We want 2 b's out of the 3 spaces. It's just going to be 3 choose 2 once more. Same thing if you have a tree. You want all a's out of the 3 spaces. That means you're going to get 3 choose 3. And this is why n choose k is in the binomial formula. This might not have made a lot of sense, but this is really the kind of thing where you need to go through it on your own, in your head. Just use this as a guideline, and then it will hopefully make some sense. And then the binomial theorem makes a lot of sense. We understand why we're taking a summation, obviously. We know that the coefficient of each term has to be n choose k. We know that the degree of each term has to be n, so that's why I'm saying n minus k and then k. So what we're actually doing with this factor here is that we're taking all the possible combinations of powers of a and b that give n, but different orderings of the same powers are not counted. Okay, so for the final part of this video, I'm going to try to explain what the problem of points is and what its solution is. The problem of points is a famous problem that was quite hard to solve, and when it was finally solved, it started a lot of serious research into probability theory, and we say it started modern probability theory. Before this problem was solved, random events, a lot of random events, were kind of seen as a divine spiritual thing. Alright, so say you have two people sitting at a bar, player 1 and player 2. They're playing a game of tails and heads, and player 1 currently has 8 points, player 2 currently has 7 points, and to win you need to get 16 points. Before they started playing this game, they had one of the cook's meals, and it apparently had some infectious, horrible disease that makes people's arms fall off. So both of these guys' arms, they just fall off out of nowhere. And that means they can't continue playing the game. But player 1 would like to know what would be the chance that he would have won if they continued on playing, and then he might be able to prove that he would have had a larger chance, and therefore he should get the money. Alright, so let's see if we can actually solve this problem. I've changed the objective from 16 points to 10 points just to make it easier and easier to visualize and explain. In the start, player 1, he needs 2 points to win, and player 2 needs 3 points. Let's just say that the first coordinate denotes the amount of points player 1 needs to win, and the second coordinate denotes the amount of points player 2 needs to win. If player 1 is to win that round, he needs 1 point, and player 2 still needs 3 points. If player 2 is to win, then player 1 needs 2 points, and now player 2 also needs only 2 points. You can kind of continue making a form of decision tree like this, and it gets very large very quickly. So I'm just going to focus on a specific subtree, and that subtree is when player 1 needs 1 point and player 2 needs 2 points. I can go out here and say, okay, player 1 he wins, so he needs 0 point now, and player 2 still needs 2. We could go along here, and that just becomes 0, 2 again. And this here, it actually becomes not 0, 1, but 0, 2 again. Because player 1, he has already won this game. There's no reason to count down the amount of points player 2 needs, because player 1 has 0 here. He's already won. We could go down here and say 1, 1. This could then go into 0, 1, or 1, 0. As you can see, after 2 rounds have passed from this position up here, there's a 0 on every point, and that means that after 2 rounds, a player must have won, or you could say that after 2 rounds, in every timeline, a player has won. To find the chance that player 1 will win, you just say in how many timelines does player 1 win, and then you divide by the total amount of timelines, which in this case is 4, and in 3 of these timelines player 1 has won. So you just say 3 divided by 4, and that is the number. Alright, so what we just did was look at one single example. What I now want to do is find the generalized formula for calculating the probability that player 1 would have won if he needs A points to win and player 2 needs B points to win. So we can't just draw out the whole diagram because we don't know how large these are. It would be an infinitely large diagram. But we could just, for help's sake, try to draw out like the 2 first branches, and this would give us this here. Now, as it says down here, we need to find the amount of timelines where player 1 would win in the final round. And what they mean by the final round is the round where someone in every timeline has won with certainty. To find this, we just need to find the maximum amount of rounds that can go before we have 0 in one of these 2 positions here. As we can see here, every single round, either A goes down by 1 or B goes down by 1. This means that the maximum amount of time before we have 0 here would be taking A to 1 and then taking B all the way down to 0 after that. So A down to 1, that's A minus 1 rounds you need for that, and B down to 0, that's B rounds you need to do that. So the amount of final rounds, that's just A plus B minus 1. That is not bad at all. Love it. Now, when we know the amount of final rounds, knowing the amount of timelines where player 1 wins in these rounds is actually not that hard, because every single round there is a chance that his number pool here will go down by 1. And there's a plus b minus 1 rounds, and he needs a rounds where his number pool goes down by 1. So he has a plus b minus 1 like open spots to pick from where he could have his number pool go down once. So this is actually just combinatorics. We could calculate the amount of ways he could have gotten 4 just by saying a plus b minus 1 choose a. This is wonderfully easy when you think about how complex the problem is. But we're not quite done yet, because as we saw earlier, player 1 doesn't need to win in the final round. He could also win much earlier, like up here for example, and then this whole branch would belong to him. Now, to do that, we just need to say, okay, he could have also gotten 1 more point than he actually needed. What's the amount of ways he could have gotten a plus 1 points, the amount of ways he could have gotten a plus 2 points, a plus 3 points, and so on and so forth. And what you then end up getting is just a sum. You would say this here plus, again, a plus b minus 1, now choose a plus 1. And then you can just continue this, and we get this. This here is the numerator. Now we just need to divide by the amount of timelines in the final round, the a plus b minus 1th round. And that's easy because we know that every round the amount of timelines increases by a factor of 2. So we just say 2 to the power of a plus b minus 1. This is the full formula. Let's again say we have 2 players playing a game of tails and heads. Player 1 has 3 points, and player 2 has 4 points. They need to get 6 points to win the game. What is the chance that player 1 will win? Well, let's just start off by writing out how many points they need. Player 3, he needs 6 minus 3, 3 points, and player 2 needs 6 minus 4, that's 2 points to win. This means that the total amount of rounds that must pass is 3 plus 2 minus 1, that is 4 rounds. That means we need to go down to the 4th row of Pascal's triangle to find the numerator. So we just say 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, and 1. Now we just start at the 3rd element in this case and go down to the a plus b, the 4th element. And that's, of course, going to be this element. So we just do these 2 ones, and we take their sum to get the numerator. This gives us 5. Then to find the total amount of timelines, we said that was going to be the total amount of rounds, 2 to the total amount of rounds. So it is 2 to the 4th power. Which gives us a 31.25% chance of winning.